Hello. I will stop my stream if you stop share. Yes. Hi, how are you doing?
Hey, good. Good to see you again.
Good to see you again. Thank you for volunteering.
All right, not a problem. Not a problem at all.
I have seen your sheets. We're in for a very nice presentation.
Oh, I made a lot of slides, so we'll see how we can do with the most, the biggest enemy of us all, which is not Corona, by the way, but it is time pressure. So
time pressure. Then I will let you start. I will leave the stream.
All right.
So at the end of the stream, we will do the questions.
Absolutely.
Okay.
All right, I'll take over.
Yes.
All right. Yeah, welcome. The Dutch user group meeting for LabVIEW. As Pascal already mentioned, it's about LabVIEW programming, but it's also about measurement techniques and everything which is related in the field of test and measurement. So today's session, the 22nd of July, that's your poor man's approximation of pi, just for the tech nerds among us. All right, I have a lot of slides, and we will go through them at a fairly high pace. We'll see how we do with the time, and let's get started. So, my name is Martin Vernout. I am currently a teacher mechatronics at the mechatronics department of Fontys University of Applied Science here in Eindhoven, the Netherlands. I'm also a principal engineer at DIGITIZER Semiconductor. Of course, this is on my own title, and it's just that you know a little bit about the background of me. All right, the presentation outline. Today, I needed to give the speech a talk, and it was lessons learned about data acquisition for the practical engineer. And that practical engineer means that you studied the theoretical part, you did practical training, you dare to experiment, and you love the insight. So you can gain insight by doing experimentation and trying it not from the abstract, not from the math point of view, but really looking at the results and trying to figure out what's happening. Everybody, or most of you, might already have used DAQMX, the data acquisition driver from National Instruments. It's fairly easy to start acquiring signals and take some measurements. There is much more to taking a measurement. We talk about quality, about what you're trying to accomplish, what you gain from it. And in this talk, I will definitely discuss a little bit of theory, give a lot of attention. So tips and tricks, they are on a lot of slides actually. All right, so always at the beginning, we start with a disclaimer. So I will definitely open and show you a lot of open doors. Based on your background, most of the material is already known for you. Otherwise, you might find some slides interesting. I'm hoping actually that by the end of the presentation, you have found at least 3 things that you either already knew and now it is confirmed, or that it is new, or that it gives you just a hint of new insight, a different way of looking at it. I know there are many slides and I have used simplifications. I definitely have omissions. If I make mistakes, they are mine alone and I'm alone to blame. And if you think that I did something really smart, I must have seen it somewhere else. So don't credit me for it. Every presentation should at least be, in my opinion, as a teacher, be inspiring, entertaining, creative. I'm making mistakes, and it is a bit of storytelling. And that's actually the joy of presenting. So if you are going to attend a user group and you're going to present yourself, don't worry, everything is okay, as long as you're trying to convey a message, what you've done in the past, the problems you faced, even this is what I did wrong, can be truly helpful for other people. All right, so the fair use is, I use a lot of material on these slides and I have no clue on where it came from. So I'm using the fair use policy. That means if I found it via Google, I can probably find it back again. But it is fair use, non-commercial, and freely distributable. All right, so let's get started. Measurements. The topic is about measurements, and no measurement is exact. Whatever you do, it will always be an approximation of something which is real out there. That also means that if you have no clue on how exact your measurement is, your result might be worthless. If you cannot base a high quality decision on it, it is as good as an informed guess, as Walter Lewin posted, and I put here his quote, to the best of my knowledge. So if you can't measure it, you can't improve it. That's the opposite side. That's why we measure. We measure so we know that we're doing the right thing, or we measure so we can get a truly good value on how to make it better. What kind of signal processing do you need? Right, so doing measurements the right way is our goal. So if you do not care about the accuracy and the meaning of what you just measured, then everybody can call themselves an expert, and it's fairly easy to get some data into your computer. You've done a measurement. Wow, you're on the roll. Well, in the real world, and that's maybe the downside of it all, you will find that there are many more things which can magically, which are going wrong, than magically go right by themselves. And that ultimately goes into the quality of the measurement. You need to do a lot of things right before you can actually prove to yourself and to others that the measurement is of high quality and you can make the decisions you want with the data. All right, the agenda for today. It will be a connection of topics. I have some words about the DAQMX driver because this session will not be about DAQMX, but it will definitely use DAQMX. We do a bit of sampling theory, multiplexed ADC, accuracy, precision, and resolution, and then some examples which go through the process of which mistakes can you make, how can you make it better, DC and AC estimation, frequency analysis, transfer function as a large example. We spent most of the time in there, and signal insight. All right, DAQMX. If you've not learned, if you've not used DAQMX before, you probably haven't used a data acquisition device from National Instruments. So the moment you start using a multifunction I/O device or some analog input module, you are going to use DAQMX or the traditional DAQ driver. It's a simple and intuitive API. It has a flat learning curve, and there are tons and tons of examples out there on how to do the things you want to do. That means if you want to get started with DAQMX, visit the ni.com website. There are great articles on how you get started, 10 functions that do 80% of the work, advanced programming, the manuals are there, and example VIs. The moment you install DAQMX, you probably are entitled to a lot of examples, and please have a look at them. They are created for a reason, to educate you on how to do it. So DAQMX is a very capable and robust driver for any hardware, and today we will only be scratching the surface. Don't worry, we will only look at analog input and analog output, but it's not the focus of today. We will be using DAQMX, but it's not that you will be learning everything there is to know about DAQMX, because that will not be fitting within the time slot. And we're not diving into special type of sensors and calibration procedures. We keep it easy. But still keeping it easy, there is lots to learn. And let's start by a little bit of theory on sampling theory. If we talk about sampling, we talk about digitizers. And digitizers, they perform sampling. Sampling is the process of generating the discrete time samples from an analog signal. Whatever the analog signal is, that means it's continuous in time and in amplitude. That's the analog part. And it's going to create specific samples in time. Sometimes very fast, millions of samples per second at a steady pace. Sometimes very slow, maybe once a minute, maybe once an hour. You could still call that sampling, of course. And the main workhorse there is your analog to digital converter, your ADC. And that's how we will abbreviate it. The output code has an error compared to the analog continuous input signal because it will be a finite number of levels which it can identify. The resulting error in the approximation of the analog continuous signal will be your quantization error. And there are many things which can go wrong. We can have an offset error in your analog to digital converter. That means the code coming out does not reflect the actual level, but a little bit of plus and a little bit of minus. You can have gain errors. That means if the value is doubled in the real world, it might be more than doubled or less than doubled in the math domain as a number. We can have non-linearities or linearity errors. And they are often expressed as integral and dynamic INL and DNL. And we have problems with settling time, that if you do something really fast, it might not be a precise, accurate representation of the value of that analog signal at that point in time. So if we have errors in the value, we can also have errors in time, because if you sample at the wrong time, and your value, your signal in the world is changing, you're looking at something which is not linked to the time slot. So we can express it as a level error, and that means the number of bits, the number of quantization levels in your ADC actually is also linked to the amount of jitter, time variance on your sampling clock. Every or most of the analog to digital converters actually operate with a track and conversion cycle. That means for converting the signal, the analog signal to a digital signal, it requires time. And in that time, you don't want your analog signal to vary. And that means you sample it, you keep it the same, and then you move on. This periodic freeze needs to be very accurate and fast, otherwise the conversion result will suffer from it. And that also means that there might be a little bit of settling and kickback to the driving circuit. Well, normally this is taken care of by the vendor of your digitizer, of your ADC or multifunction DUG board. Sometimes you actually see the results of this track and conversion settling time back into the measurement specification. So, in a nutshell, we go from continuous to time and level discrete. We sample at specific points in time. In here, over here, it is actually, let me put on the laser pointer here. It is actually collecting data at specific time points here, T1, T2, T3, and T4. And also the level itself is now quantized. That means we need to talk about ADC resolution and quantization error. And the resolution of a converter simply indicates the number of discrete values it can produce. And by a stroke of luck, we're using in digital, we use almost everywhere the power of 2. You will find that the number of quantization levels, the number of discrete values which can be produced from an analog input source is always expressed as 2 to the power of something. And that something is the number of bits in your ADC. Now, if your ADC can convert signals from 0 to 1 volt and you only supply 1 to 2 millivolts, you're not using your digitizer, you're not using your ADC to the best possible outcome. So what do you need to do? You need to get your signal into the range of your analog to digital converter. So either you change the level of your ADC, your reference level, which is often not operated that way, or you amplify your input signal. That's how easy it is. So if we are starting to sample, we know some errors are to be made in the on the vertical axis, the value axis. We also are looking at time sampling. And it is important that for a faithful reproduction of the original signal, that's only possible if the sampling rate is higher than twice the highest frequency of your signal. Otherwise, you're undersampling and you might not know precisely what your signal looked like. And most of the signal processing actually assumes that you're sampling fast enough. And there is always a downside. If you sample faster than fast enough, you have more data, so you need to compute more. Other problems are if the bandwidth of your input circuit is higher, you get more noise, and you pay probably more for a fast digitizer than for a slow one. All right, so we talk about signals which we are going to acquire, and for that we have signal to noise. The signal to noise basically says how good is your signal over or stronger than the random fluctuations which you cannot control, and all those signals are actually named noise. A good signal, that means there is no noise in the background, or it is not influencing your measurement in a very poor way. If you do that on an ADC, because that's making an approximation of your input signal, it's making a tiny error each and every time that looks like noise, and your signal to noise ratio is at most that formula which is given over there, and it's expressed in decibels. So the 1.7 plus 6n gives you a rough estimate of the accuracy which is inherent to all the ADCs. It will never be any better than that value. So if you need 90 dB, you can at least approximate the amount of bits, effective number of bits you want from your digitizer to work. So we are sampling, and what happens if there are signals which are above your NYQUIST frequency, which is half that frequency where you are sampling at? Well, if there are frequencies over there, for example, over here, that noise spike on the right side of your NYQUIST frequency, which is half the sample frequency, that one will actually be mapped back within the fundamental range to your NYQUIST frequency, and you cannot tell the difference. You don't know if it was actually there or that it was coming from somewhere else. We call that aliasing, and the moment you have digitized your signal and that alias exists, there is no way that you can remove it again. You don't know where it came from. But let me explain that in the next slide, please. So if the continuous frequency domain looks like this, we have a couple of zones, zone 1, 2, 3, 4, and they are in half multiples of the sample frequency. What we actually are looking at from a measurements perspective is only at that first zone. But it means this is like a fold-up system, that if there are signals in zone 2, they fold back, and they fold back actually mirrored. Zone 3 basically gets overlapped with zone 1, zone 5 gets overlapped with zone 1, zone 4 gets overlapped with zone 1, but mirrored again, and that means you're looking at this. Now, how do you spot your original signal where you know that your signal should have been, which is in the range of 0 to sample frequency divided by 2, your NYQUIST frequency? So there is one simple solution. We need to get rid of all these higher frequency terms, and we do that by low-pass filtering, or we can change it by increasing the sample rate. So we call that first zone the baseband signal, and that has frequency components which start at DC, F is 0, and extend up to some maximum frequency. Two solutions, low-pass filtering and increasing the sample frequency. And if you do not filter, and you know that there is some aliasing to occur, you can basically estimate what your measurement resolution will suffer because of that aliasing effect. And if you then still say, I don't care, well, then that's your measurement. You take the penalty of aliasing signals getting back into the baseband part. All right. So analog to digital converters, part of your digitizer. What else can go wrong? Well, what else do you need to do? You need to connect your physical real world signal there. And there are various ways to do it based on differential single-ended, reference single-ended, non-reference single-ended, floating signal sources and grounded signal sources. And if you mess up, if you do not use the right one, you will get a not optimal result. Sometimes you sacrifice a little bit of that because it's just easier to connect a reference single-ended signal and then have many of them. Sometimes you want best, and then you might go for differential signaling. All right. So there are a lot of things which actually can go wrong, and you need to care about if you want to take your first measurement. Let's go for an example of a multiplexed ADC. So we have one digitizer and we have 5 channels or 10 channels we want to measure. So what we normally put in front is a multiplexer. That's a fastly operated switch, which will make sure that your ADC is connected to channel 0, channel 1, channel 2, channel 3 in a specific order which you might be able to program. If you do that, your channels all need to be of the same amplitude. Your signals need to be strong so it matches the ADC input range, or you want to have a gain stage in the middle which can adapt to the range you specify for that channel. And approximately that looks like this. This is coming from an M series National Instruments Data Acquisition Multifunction Data Acquisition Board. And well, over here, obviously, we have the ADC. That ADA spits out a lot of data, which needs to be buffered a little bit before it can be transferred to the main memory. Before the ADC, we have a programmable gain instrumentation amplifier, a connection circuit, and a multiplexer. That multiplexer makes sure that the signals you want are fed to the ADC. So one ADC does the conversion for multiple channels. Obviously not at the same time. It needs to do that on a sequence base. So if you're doing that, we call that actually scanning. Sometimes that programmable gain instrumentation amplifier needs to adapt to a new signal each and every time it hops from channel 1 to channel 2. And therefore it needs to settle, it needs to get stable, it needs to actually do what it is supposed to do, and that is a gain multiply, a gain factor multiplied by your input signal. And it normally takes time. We call that settling time, and therefore if you have a fast system and you make it run a little bit slower, it might be a little bit more accurate because it has the time to settle to the desired value. Now, multiplexers contain switches. It's a fast switch, and that leads to ghosting. If you ever run into this one, you know probably what I'm talking about. But it looks like that 2 channels, they have something in common. Channel 1, which is sampled slightly after channel 0, for example, might be influenced by what happens on channel 0. So channel 1, the measurement result, but even the actual data in the real world is influenced by what's happening there in channel 0. And that's because of charge, accumulated charge in your switch, which gets moved around. And the easiest way I can make it make you look at it is over here. We have a mux between channel 0 and channel 1. They are sampled to the ADC in the gain stage periodically. That means first channel 0 is sampled at 3 volt, then the switch is operated to go to switch to channel number 1. And a little bit of the energy it picked up from the 3 volt is now being pushed to channel number 1. If I connect a capacitor over there, which is of course a strange thing to do, but it's just a high impedance source, a little bit of that charge is actually going to charge up or charge the capacitor, so the voltage on channel 1 will grow. And it's really this what is happening. That charge injection is a pain in the butt. It's just what it is, and you get it for free if you have a multiplexed analog to digital converter. So this is what you get. Now the problem, of course, is will it be noticeable in your final application? And most of the times that's not the case, because this is a high impedance source. Normally you drive an analog digitizer with a low impedance source. So it's a strong voltage which is reflecting what you have measured, probably by adding an op-amp, a buffer, or something like that. But if you happen to measure high impedance sources, ghosting becomes apparent, and there are some ways that you can find out if you are suffering from ghost. So how do you know if you're hunted by a ghost? First, change the level of the previous sample channel and see if that makes a difference. And number 2 would be change your sample rate, because that charge injection happens at the sample rate. So if you run it for 10,000 times a second or 50,000 times a second, when you operate it at 50,000 times a second, the charge which you're moving around from channel 0 to channel 1 is 5 times as large. So that will speed up the increase of the voltage on the capacitor 5 times. Simple as that. So if you have more money to spare or more money to spend, or your measurement needs it, don't use a MUX, go parallel. And there are also boards which have multiple analog to digital converters for most of the channels. So they are called simultaneously sampling. And that means they can sample actually at the same time at the expense of having more ADCs. Good. Give attention to. I told you this was about theory and a lot of give attention to. Use low impedance sources. If possible, make sure your driving circuit on the digitizer is low impedance. So it can drive relatively high currents. Then ghosting goes away, and it also makes the signal a little bit more robust. Use short, high-quality cabling, because everything you cable in the outside world is sensitive to crosstalk, pickup, etc. So keep it short. And the capacitance of the cable can increase the settling time if it is not driven by a low impedance source per se. Carefully choose your channel scanning order, because with a multi-channel multiplexed ADC, we are switching from channel to channel, and we might be switching the gain as well. And if we're switching from a large to a small input range, that increases the settling time for that channel with the small input range, so the high gain. Avoid scanning faster than necessary, so you don't end up with too much data, or that you are picking up more noise because your bandwidth is now higher. Make sure you sample faster than the NYQUIST sample rate if you need to reconstruct your signal accurately. Not always needed, but if you want to look at your signal in a frequency domain and you want to really know what's happening there, make sure you're fast. And you can add a low-pass filter to remove the high-frequency signals, which is often called the anti-aliasing filter. Right, electronics to the rescue. What we suffer from most are ground loops. That means your ground, that's the 0 volt node somewhere, that is not taken lightly. If this is your ground node and we have connected multiple paths, every bit of trace has resistance. They actually sum up in the resistance they have in common. So careful that you don't create ground loops. Now, in the past, people would have said ground loops, yeah, don't make sure that you have a high current flowing through a common resistor. But high currents doesn't mean high power. High currents also come into play if you take a small capacitor and you drive it by a digital pulse. So something which is changing fast in number of volts per time unit. So high DVDTs cause large currents, and if those large currents go to a common resistor, that voltage drop across R2 in this case will actually be picked up by your measurement system. So avoid ground loops, and there is a lot of documentation out there on how to prevent ground loops. Inductance is also not your friend. If you have a little bit of inductance in your return wire, for example, over here near ground, now each and every wire you create which carries a current will also be a little bit, will also have a magnetic field, and therefore it has self-inductance. If you have self-inductance, so it's not if you have it, you always have it, that can lead to ringing and strange oscillations. Now, by adding a resistor in series, you actually dampen it, you make it slower. And if you make it slower, at least the signal is not so super wrong. Also look at the vertical scale here. If you dampen it, the measured voltage goes to 3.3 volts. If it oscillates, because there is some energy stored in the inductance, you will see that the measured voltage can even be higher than your final voltage of 3.3 volts. It cannot effectively be double. So you don't want to have inductance, so make sure that there are low inductance traces in your measurement system. Over here you have the combination of your resistance and inductance part. So if you make a ground node, a star point grounding, you're all the better off. That's the way to go. Coupling is because there are high DVDTs and high DIDTs, changes in voltage and changes in current, they will cause coupling into your circuit. So the simple solution is prevent too high DVDTs and DIDTs. High speed is not positive at all. Better make the signal a bit slower with slew rate control, for example. And careful, make sure that your layout is in line. You could use twisted wires. They are not strange at all. They actually were invented by Alexander Graham Bell a long time ago. And it's a very cheap solution to counteract the influence of magnetic fields. So very fast, no, just fast enough, please. Make it slow down. And we have sometimes problems with transmission line effects. Read it later. So give attention to short wiring, proper shielding. Make sure that you do it in the right measurement mode, single-ended, differential, break your ground loops, reject common mode noise, and root cause the crosstalk and solve it. Because if you leave it there, you do not have it under control. So that leads to the first conclusion there. Don't take a measurement for granted if you want the result to be meaningful and not indicative. Do not make expensive decisions on poor data. Sounds like an open door. I think it is, but it's good to state it anyway. Well, read this tip later. It's about reading the manual, and I think you should do it. It's free information. Right now, I've talked about accuracy a couple of times, and I think it's more important to understand what it actually means. So what actually do you actually need for your measurements to become good enough so you can make decisions on it? What constitutes a good enough result? Sometimes you do not need an absolute accuracy, but relative accuracy. And therefore, we have logarithmic converters. And a logarithmic converter can do something very smart. It can have a very high dynamic range converted to a smaller range by the sacrifice of moving an absolute error to a relative error. So for example, this one, it can measure current from 100 picoamps to 10 milliamps. And now with simply adding a cheap ADC with a fixed gain, you can actually measure currents over a vast amount of range, up to 10 milliamps. But it will not always be a perfect representation. It will be 1 or 2% error. So you can have a low current measurement, 2% failure, but you can also have a high current measurement of 10 milliamps with a 2% error. So the error remains the same relatively. In an absolute sense, obviously it changes by the range. All right, so from now on in this presentation, everything we do is not suffering from analog issues anymore. We've done our job. Let's look at the data. Accuracy, precision, and resolution. Accuracy is the error between the real and the measured value. So if you look at this this blazoon, this target, you want to be in the center, obviously. That will give you a high accuracy. Precision is the spread of so this one in the quadrant number 3, that gives you not a lot of accuracy because it's obviously not in the center of the target, but they are nicely grouped close by. So that's good repeatability or good precision and bad accuracy. And resolution is how far are you off the center. If you measure that in centimeters, centimeter will be your resolution. If you measure it in millimeters, that will be your resolution. So precision is linked to repeatability. How do you improve the precision? Well, the precision of a measurement can be improved by oversampling. It's a bit odd because if it spreads, but if you average, a lot of the spreads will average out, and that's called filtering. So most of your measurements you do in the real world are normal or Gaussian shaped, and you know that such a distribution like this is always presented by a mean value, the average value, and your standard deviation. under the constraint that we have made enough random measurements, we can now estimate the real world spread. So if I measure 5 times an arrow, I can actually calculate the mean. That's the center of the arrows, and I can measure how far they are grouped apart, and that will tell me if it is a normal distribution or not. Now, most things in real life, because of the central limit theorem, are normally or Gaussian shaped. So sometimes we just need to add that as a given. So we could do is repeat a single shot measurement. If you're doing a repetitive single shot measurement, the first thing is, was the distribution actually normal? And you can test it. Just put your data into a VI, and that will tell you if it is nicely skewed or not skewed at all. The target value should be 0, and the kurtosis should be around 3 for a normal distribution. So it's not something to take lightly. I am assuming it's a normally distributed data. You can test your assumption by measuring it. So what happens if we move our 50 data points, for example, to 500 measurements? Well, we get a better indicative value of the spread. So if I take a low number of measurements, I know that it's approximately 5, and I'm not still sure what the underlying distribution is. If you take more measurements, the shape will be more noticeable. Okay, but taking a lot of measurements, of course, yeah, there is a penalty to pay for that. What we could do is, instead of repeating that 1-point measurement, we take a multi-point measurement. That means fastly collect data, let's say 500 samples, and not look at the distribution, but only at the average value. If we do that, all the values reported, there are less values reported because you've now collected, in this case, 100 samples 50 times instead of 1 times 5,000 measurements. It looks like the spread is less, but you can still calculate the standard deviation of the parent population, because your average will always look distributed smaller, tighter together. So that's the statistics 101. If you want to know something about the measurement resolution you have, it's sometimes linked to the number of measurements you take. Sometimes that's something you can do, and not always. But if you want your measurement to be twice as accurate, you need 4 times as much data. If you want to have it 9 times more accurate, you need 81 or squared number of measurements to make that happen. So it's inversely proportional to square root of n. So keep that in mind if you want to think about quality measurements and you want to make it into the real world. So what happens if you have too low a number of measurements? Mean value and standard deviation with the bell-shaped curve of the Gaussian distribution tell you something about the confidence level. If you have not enough data, then you can't use plus or minus 3 sigma, for example. You need to do that in a different way. Therefore, you have the student's t distribution. And that leads to an important reading tip. If you have not enough data, or you're measuring only a couple of samples out of a big population, you make errors, and they are hard to spot at first, but there is a good document on the web. It's called Measuring a Small Number of Samples and the 3 Sigma Fallacy. Please read it if you care about the quality of your measurement and you're not sure if you're making enough measurements anyway. This document is actually tailored to semiconductor industry, but I think it's more generally valid outside of that. So, know your basic statistics. If you measure and use results for further processing and decision making, you should be familiar with at least the basics. Estimating AC and DC signals. Very simple example, still something to learn here. Let's say we have a signal in the real world, which is a DC level plus some AC variation. Right now, it's nicely shaped as a sine wave, That's the most ideal case, of course. And you can understand that if you collect a lot of samples between time step 1 and time step 2, and you sum all those values and divide by the number of samples you've taken, you get an average value. That's the definition of an average. But because that sign is strongly going more positive than your average and lower than your average, that average is actually influenced by how you end or how you start and end. So how do you measure or how do you differentiate the DC from the AC? Well, that cancellation is not perfect, so you could do something very simple. Acquire more. Because if you acquire 1,000,000 times that sine wave, the influence of that last sine wave, which is sampled high or low at the end of the period, is not so important anymore. So you get diminishing influence of that last bit of sine wave. But of course, your measurement time increases drastically. And there are smarter ways to do this. The smartest way is apply a window. If you apply a window, and that window function is always symmetric, and it starts and ends with a 0. So over here, your window function is that nice, it almost looks like a Gaussian shaped normal distribution curve. That multiplies your incoming signal. And then you have that strange peaky signal over there, which, well, basically familiar, looks a bit familiar, like a mountain or something. But then seriously sign inspired. Can we then calculate it? Yes, we can. We focus more on the middle, so the end effects are not used anymore. And by multiplying by the coherent gain and the equivalent power bandwidth, you can estimate your DC and AC value. So the first step would be calculate, multiply by that filter, calculate your mean, subtract the mean from the original signal. Now we only have the sine wave left. There we apply the window again. We sum everything up. We do the RMS thing. So we actually calculate the root mean square, and ultimately we estimate what the AC value is. And that works great. It's a standard VI when you buy LabVIEW. So use it. Rules for improving your DC and RMS accuracy. Follow the hints. So how much do you need? Well, you need a couple of sine waves. You need 3, maybe 5. If you use a different filter, a low side lobe filter, for example, you can actually get 6 digits of precision if you have 5 sine waves sampled. So it correctly predicts your DC and your AC. And yeah, if you don't do it, you only have 1.5 digits of precision, which is, of course, poor. Alternatives? Yes, there are always alternatives. The first one is find or convert to the frequency domain, basically operate an FFT, and then go and search and collect the power, and then, well, basically you know what the frequency is and what the level is. Right, challenge alternative solutions. Sometimes you have a solution and you say, well, it's giving me okay-ish results, but there might be a way better solution for that. It worked for me in the past. Prevents you from doing it better this time, because if you made it okay-ish in the past, you're happy with that okay-ish carrying on in the future. So discuss with your peers is for sure a good way to open up for improvement. Effectively, as a teacher, I can always tell you that the process of communicating an idea, even if you don't solicit feedback, will help you clarify and see it in a new way. And a famous quote I always use is, why do good ideas prevent even better ones? Because you get stuck on the good idea that's prohibiting from making the leap to a better one. All right, short sidestep for DAQMX. What we are going to do is we have a couple of examples ahead of us. And they will start by configuring a channel, then checking for how many samples are available. If there are not enough samples available, we're going to delay for some time, then read the data and process it. That's a simple loop, and it looks a bit like this. So this is actually what DAQMX looks like. It's a collection of VIs with a lot of constants of controls connected. Most of the things you start with, like range, min, max voltage, or sample frequency, or what's the size of my buffer, they are actually just a request. DAQMX knows better. It will adapt to your hardware need, or it will check what is the capability and what is smart. So there is some logic behind it. If we are collecting data, we check how much data is there. We actually can calculate how much we need to delay for the rest of the data to get digitized. Then we simply read it. We do something with it. In this case, we just print it on the screen. We make a graph out of it. And we loop continuously, because the moment we start acquiring data, you probably want to read it as fast or faster than it becomes available. If you don't, you end up with data in memory, which gets filled, and then it will abort by an error. All right, so if you operate this one, you can actually find that by the amount of processing time you input, you will see some strange oscillations by Windows or the DAQMX driver. And the simplest solution here is make sure that if you're using buffers, make them large enough. Windows is not super smart. DAQMX is a smart driver, and it has some game plan of its own. If you think it should be good enough, do not assume, but verify the assumption. If you think your buffer is large enough, put it to the test. Put a VI next to it, which is computing or cycling as fast as possible, or start installing Office if you're acquiring data. If it's still working after the installation and it didn't find a problem with you did not read the data fast enough, then probably your buffer is good enough. To improve yourself, we must not forget to verify that the assumptions that we made can be verified, and keep them in mind. All right, let's do something fun. Let's go for the signal time frequency equivalence. Any time domain can be described as a sum of scaled shifted sine waves of different frequencies. This is what the Fourier transform gives us, and we benefit from that greatly within signal analysis. So the FFT is a lot of things, but the most important one is it transforms your time signal to the average power per frequency, and so you lose your time position info, but it assumes that your time signal is periodic. Periodic means that if this is what you have captured, the underlying math of your Fourier transform actually assumes that it repeats infinitely, and then you see this big discontinuity over there. And as a general rule, all signals with an abrupt change, discontinuity, will create high frequency components. You need a lot of sine waves working together to make this jump actually happen. So we have windows. Those Windows functions are actually the same Windows functions we've used for the DC and AC estimate. Each window has its own characteristics, and there are so many windows that they are, well, they all make it better, but they are there for a reason. So for example, if we have closely spaced sine waves, then you might want to go for a uniform window, which is no window at all, or a Hamming window. If it is a sine wave or a combination of sine waves, a Hamming window will normally suffice. May the best window win. Yeah, there are many windows, and it's always a trick on how to think. Did I prove that I've chosen the right one? So the FFT. If you perform an FFT, your time domain signal will become a frequency domain signal, and the spectral line resolution will be divided by the number of samples in your set. Let's see, zero padding. Zero padding, that's adding zeros to your signal, which seems to increase the N. And if the N increases, your spectral line resolution gets lower, so you get more if you add zeros. But often when it sounds too good to be true, it's not true at all. You actually do not gain any additional resolution. It just looks that way. So what can we learn from looking at the frequency spectrum? Over here, I have a simple setup with a signal generator, a data acquisition board, and a gain stage. And if I short the input and the output, this is what we measure in the frequency domain. So low values, minus 120, means there is almost no power. This is actually the ground, the noise floor of that digitizer. If I only keep the input shorted, so the output is actually driving it, I see a little bit of DC and a little bit of signal being picked up from somewhere else. If I apply a 1.9 volt signal, but I still input, I still short the output, I see a little bit of leakage. This is there should be nothing being picked up because the output is shorted, so this is probably linked to grounding. If we have a small signal on the generator part, you see at least a lot of signal over here, which is way more than the ground, the noise floor, which we had with shorted in and outputs. So that's coming from our generator. That means not that our generator is very bad, but it means there are some spikes above the noise coming from the generator, and you need to understand that this is the quality of the generator. It also shows you that there is a strong third harmonic. That means if this is the fundamental frequency at 3 times that frequency, we call that the harmonic, we still find a little bit of power. And if we make the signal too strong, so if we apply more than 2 volts peak peak on an ADC, which is capable of sampling 2 volts peak peak, you see a lot of higher frequency components being created, and that's because of clipping. So it does not look like a sine wave anymore, and then you need higher frequency components to counteract. So what did we learn from doing that simple FFT? Well, what we have learned is that the data acquisition system seems to be clear. The function generator, the function generator is the major source of frequency content. There is some pickup, and your generator has a strong third harmonic. Be careful with the output level. We could not have done this if we just looked at the time signal, because those signals measured here are so tiny that they are in the random fluctuations in a couple of LSBs, a couple of least significant bits of your ADC. So the final example. The final example is I have a small amplifier. It does amplify 2 times or 6 dBs, and there is some frequency dependent gain. And actually the goal is, let's measure the transfer function in order to grade if the amplifier is okay or not. We call that a Bode plot. This right side, the frequency and phase transition of that amplifier, we call that the Bode plot. And the Bode plot graphs the frequency response of the system for magnitude, amplification, and the other one for the phase. Now, if you want to measure the gain, you estimate the response amplitude, compare it to the input. So if you do that, you need to measure both the stimulus and the response, both the in and the output at the same time, or nearly at the same time. And with DAQMX, we do that by operating an analog output task, which we run in synchronous to the analog input sample clock. So the moment the analog output starts, the analog input is running as well, because actually it's the analog input which is making sure that the analog output gets clocked, and then the waveform presented there will be outputted to the real world. So the setup for this measurement is, again, I have that multifunction data acquisition box. I have my op-amp, I have a power supply, I've connected the wires. Let's see what happens. If you're running, by the way, analog input and analog output at the same clock, you might be worried about settling time, and therefore you can operate the delay from sample clock delay setting of DAQMX. Have a read later. So the first solution would be very simple. The first solution is I create a discrete set of frequencies, and it's called a multi-tone series. So my waveform, which I'm going to generate, is a sine wave, 2 sine waves. Then for a different frequency, again 2 sine waves. A third frequency, again a couple of sine waves. And because we know that the transfer function looks like this, we don't need all the points. We just need enough points so they can be connected by linear interpolation, and it looks the same as the transfer function. So maybe only 20 test frequencies are needed. Now in this case, it shows that for the lowest frequency, you actually claim a lot of time. For a higher frequency, you have less time. And that means that your power spectral density, the amount of power which is there on the frequency axis, so with the FFT in place, diminishes strongly with higher frequency. So the power here is around minus 90. If it is over here, let's say minus, minus 30, you can estimate the ratio of power at low frequencies to the power at the high frequencies, which is many thousands of times. We created a single step frequency waveform, so there is a little bit of calculations to make sure that it is nicely as depicted here in the time frame. We actually find the frequency back within a subset of the data, and the whole idea is that we generate this, we capture the response, and we know by looking at the index, the data value index, what the original sine frequency was, and then we are going to compare it for the stimulus and the response, and basically what comes out is our Bode plot. So we find the frequency, we estimate the level and the phase. We use the extract single tone VI, which performs very good on minimal data, and we do the calculation. The calculation is, we have our two channels, stimulus and response. We might shift one of the channels a little bit, one sample, to compensate for the settling effect on the analog output. We find the frequency of interest. We perform a log operation because normally Bode plots are expressed in logarithmic terms, so we can have a high dynamic range. We calculate the phase difference. Maybe we compensate for a calibration of a pass-through of output to input. And the result looks like this. We have these dots. They are the actual measurement, and the dotted line in the background is actually the value estimated from simulation from a SPICE simulator. So that looks pretty good. And the funny part is that this is a very slow measurement. A lot of samples were generated, and most of the time is actually spent on the lowest frequencies because we needed to generate those sine waves at the low frequency part. So instead of placing them one after the other, we could run them in parallel. If we run them in parallel, it means the low frequency sine and the high frequency sines are all overlapping. And that's not a problem because our FFT will split them, will bin them out to the frequency components. That method is called multitone, and it has many benefits, but it's also more sensitive to noise. So if you look over here, you can now find out that all the test frequencies, which are actually the spikes in the FFT plot, they are of equal power. And you can actually also see that the noise is slightly increasing near the higher frequency side. So if you operate this one, you still need to search for a specific frequency component, and that just got a bit harder because in the series case, you know that in this time slot you only expect to find one frequency and you know which one it is. But if all those sine waves are overlapping, you might need to find the right one, and all frequencies are present because it's a parallel of all those sines. So that sometimes leads to some spikes, and these problems can actually be overcome quite simply. But right now, that's good enough for our proof of concept. You see that most of the points lie on the curve, and there are some very strong outliers there, and they are actually always at roughly the same locations. So instead of having a set of sine waves, we can do it in a different way, which is a continuously varying frequency, which is called a chirp, because it sounds like a bird. So it starts by having low frequencies, and then gradually the frequency increases. And if you take the FFT of this signal, you will notice that all the signal frequencies are actually present. Over here, we just generated. It's a chirp VI coming from the signal generation palette. So it's fairly cheap. I think it's always present. Our analysis doesn't need to find a frequency because all the frequencies are actually valid. we just calculate the FFT. The values go to an amplitude in RMS and a phase. We again calculate the logarithmic value 20 times because it's a voltage, the phase difference. In a very similar way, we get this plot. So instead of having discrete frequency points where we have found the transfer function, we have them now for all frequencies. In order to plot it, I have used the result from a SPICE simulation and converted it to an XY plot. So that's fairly simple to do. But if you put this into your measurement loop, which I did, you're actually calculating and converting that same string from SPICE simulation back to the XY graphs again and again and again. And we better do green engineering. So we only do that once, but it still adapts nicely to modifications you make. So it's not as a constant, but it's a constant copy from the text file from the SPICE simulation, and then it does the parsing only once. Transfer function looked great, no problem at all, but we used a fair amount of samples here, and we have a lot of frequency points for our gain and phase. So a signal with all frequencies present is the chirp, but we could also have used random noise. Random noise, or white noise, non-colored noise, is a random signal having equal intensity at different frequencies if you have enough samples, giving a constant power spectral density. But if I do that, you will notice that at the high frequencies, we start seeing some very strange spikes. It looks like the underlying curvature is there. This is actually the uncalibrated one. So on the phase side, it ends a little bit high. But yeah, I know that my measurement is approximately right. What I could do is I could filter it a little bit. And if I filter that curve with a lot of measurement points, I actually end up having this. So even when I input noise, no specific frequency content, no sine wave at all, still the transfer function comes out. But I need to apply a filter. I needed to apply this filter because my data result was noisy. The problem is, I'm not sure why I'm doing this. I could have run, for example, with only 50,000 samples with noisy data, look at the result, and I might end up seeing the artifacts of my low-pass filter on the data. If you filter something, that filter needs time to settle, and that's more pronounced on the low frequency part where there are just lesser data points in your transfer function. So I started with random noise, but I come back to it. This might not be the way to go. I need better random noise. There is a different VI called periodic random noise, which is the summation of sinusoidal signals with the same amplitude, but with random phase. And it consists of all the sine waves with integral number of cycles in your requested number of samples. And therefore, you need no window. That means if I simply replace the normal Gaussian distribution or white noise random noise generator with a specific one, I don't need any filter. I get the perfect result, and it looks like a chirp. And in this way, the frequency content of a chirp and of a periodic random noise generator are actually equivalent. In this case, your measurement time is about 0.1 second. So all the results look good. We are ready to go. Could we have done better on the gain accuracy, the phase accuracy, the time? How do we actually move from here? We could make a faster chirp. We could change the noise or choose a different method. Well, if we look from a power perspective on the frequency domain, this is the chirp. The chirp get a flat frequency response up to some frequency, which we will set as F2. If we take the PRN, it's again a flat line. It's slightly differently scaled, but it's still a flat line. So flat energy for all frequencies. That's why chirp and PRN noise perform that well. My serial test frequencies, one sine after the other, has the diminishing output level at higher frequencies. And if we do that for parallel, you get all those spikes, but we have problems with finding the right ones. That gives me a slight advantage going for chirp and PRN noise right now. But we could also have looked at the time aspect of it. If I present a pulse on the input, in this case, a square pulse, I can observe the reaction of my amplifier, and that's effectively good enough. What I can do is I can do system identification. I just provide a stimulus, I measure the response, I present the system to a model which says there are 1 pole, 1 0, or 2 poles, 2 zeros, and it will figure out what the most likely transfer function is. And if you do that, well, this is your transfer function. That clearly shows that there is 1 0 and 1 pole linked to the value of the resistors and the capacitor. And that means that if you put it into 1 0, 1 pole, this is the curve which comes out. And this is the result which comes out only after applying, in this case, I've done 5 pulses, and I've done that for 10 milliseconds of time. So a very fast response, a very fast stimulus, a very fast response, and the result is very, very accurate. Measurement time, 10 milliseconds. Also means that we can now describe the curve of the transfer gain plot and the transfer phase plot by a couple of numbers. We just need to store 3 or 4 numbers, and then we have everything we need to reproduce. So, result of identification with 2 poles and 2 zeros, well, that actually maps even better. So maybe the op-amp has a slightly dominant pole at a higher frequency because of its gain bandwidth product. So it's decision time. This is the most important one. Now, how do you rank your solution? How much time does it cost to compute the result? Do you need a license for it? What's the implied accuracy? What's the speed? What's the flexibility? Will it adapt to different transfer functions? How do you know if it is the best one? Is it a generic solution, and how robust is it to noise? This is what our job as engineers is. We have a set of viable options. Now we need to choose, and choosing is always hard. So there are some pitfalls for engineers, and one of them is spending too much time in the research phase, because we could make modifications to modifications and try to optimize the hell out of it. Sometimes good enough is good enough. Getting stuck in the perfectionism trap and mistaking your option as fixed and binary. That means you don't need to choose one over the other. You can mix and match. You are creative. You know what to do best. For example, if you don't want to measure the transfer function, but just grade the amplifier to be okay or not okay, the gain was set by the ratio of 2 resistors. The gain transition, the frequency dependent behavior, was linked to the resistors and the value of capacitor C1. You know that this type of amplifier has always a minimum gain of 1, guaranteed by the design. And actually, it has a low number of degrees of freedom. So, why not do 1 frequency and a little bit of DC? If I just make my test a DC level plus 1 frequency in the transition in the Bode plot, this is my result. I now have 1 data point at the low side. I have 1 data point during the transition. That's also there in the phase. And if I make only those 2 measurements, which I can do, for example, every 2.5 milliseconds, I check the DC gain and I check the gain in the phase at 2 kilohertz, and therefore conclude that the rest of that whole curve actually is as expected. Low number of the degrees of freedom means if you measure only a couple of points, that would be good enough. But that's only seeded by looking at the original question, which says measure the transfer function, the gain in the phase, in order to grade the amplifier to be okay or not okay. Well, if I do this short measurement, I can guarantee you that that amplifier is doing okay. There is no way that it would misbehave with that limited amount of freedom the design gives me. So design is a complex iterative process. Your initial design solution will likely be suboptimal or even wrong. Sometimes you go one step forward, 2 steps back due to new insight. I started with noise, and that I added a filter for it, and then came to the conclusion that no, this is not the way to go. I need to change my noise shape. Ask more questions. In any conversation, the process of coming up with questions to ask and listening to people's answer can lead to new ideas and insight. Yeah? Failure is key to success, so learn from your mistakes, but sometimes at a cost. Last final slides, and those are only a couple of slides. That means we have looked at the acquisition part. We collected our data. We looked at the frequency content. We know that the frequency content is identical to the time content. So if I look at the time signal over here, it looks like a very long sine wave. Still, if I convert it to my power spectrum, to my FFT, my frequency domain, it looks like nothing I would have guessed, because I would have expected one single line at one frequency, but it's actually, well, a whole lot. And there is nothing with a filter or a window I can do to make this change. So what's happening? Why is my sine wave not perfect anymore? It's because if you look at time, your time domain signal, you know the value over time. That whole block of data we can convert to frequency domain, and now we know which frequency components actually have energy. So what are the underlying collection of sine waves? In time, we don't know the frequency part. In a power spectrum, we don't know the time part. And in this example, they actually collide. And that means we need to go beyond the FFT. And for example, we can go for joint time frequency analysis. If we do that, JTFA, that same signal which we saw a couple of slides earlier, now clearly shows us the following plots. We see that the frequency is changing between a high and a low frequency in time. So it's modulated, it's moving around. And because it is modulated, we actually get the bandwidth of modulation. So this is a normal modulated, or FSK, frequency shift keyed modulation spectrum. And the shift in frequency is actually not even that nice. It's abrupt, therefore we consume a high bandwidth. If you couldn't look at your time signal like this, you wouldn't have guessed what it meant. Because if you now measure the AC signal by just finding the highest peak in the power domain, did you actually estimate the power of the signal, or is a lot of that energy being moved to the sidebands, the upper and the lower sideband of your modulated signal? So analysis beyond FFT, yes, there is much more. JTFA, wavelet transformations, they gave you more insight. And the better you know your signal, the way better it becomes to analyze correctly and estimate the values. So the full example is, it's just creating 2 sine waves of slightly different number of cycles in a block. Therefore, if you know that it exists, you can see that the frequency over here is slightly higher than over there. Well, that's hindsight. We calculate the FFT, which gives rubbish. We calculate the JTFA, and that shows us all the data insights we need. How do you know about this? Well, go to the LabVIEW Advanced Signal Processing Toolkit, look at the examples provided. You need to buy this one, obviously, or buy a book, Joint Time Frequency Analysis. Its book is heavy on the math, but yeah, such a great introduction to joint time frequency analysis. Engineering. Last tip, theory versus practice. In theory, there is no difference between the two of them, but in practice, there is. You will always find that it is slightly different when you operate it, and you might not hit the perfect measurement resolution. You need to try it a little bit, twiddle a little bit, and yeah, then there is always Murphy's Law. So all problems can be solved. You need to apply also the practical part to the theory to make sure that you're doing the right thing. Try to learn from your signal. See actually what's going on beneath the signal. Just don't calculate an average and be happy with it. Try to do a little bit more. That means, in summary, if you acquire a signal, check the quality. Always good advice. Know your signal. Analyze it until you understand it. If you don't understand your signal, you actually don't know what your measurement actually is doing. The right strategy to solve your need. Use the right strategy. You might be tempted to do something else, which under certain circumstances might be suboptimal. If you use statistics, please use the statistics properly. Do not assume, but verify if you have the time. Read the manual. It's really there for you to gain a lot of knowledge and have fun in the process, because this is the engineering cycle. You try something out, you learn from it, you make an improvement, and you're all the better off for it. So if you have questions, well, you need to first formulate the right type of questions. Use the power of many, so internet forums, user groups, get in contact with your company experts in a different field. Maybe some of the slides were heavy on the electronics. Well, contact the guy who has all the knowledge on electronics and ask him, can you help me? Because I might not be doing it in the best possible way. Take a course and learn from the experts, or buy yourself a book and start reading. That's why books are there. And that finally, at slide 139, that means I have done my job. I've run through all the slides which I wanted to present. Thank you very much for your patience and attendance, of course. And yeah, in a little bit of time, we can actually start to the main course of this LabVIEW user group, Jeff K's talk, of course. I was just the appetizer, the entree, call me the starter. Somebody needs to start. It was me.
You're saying that, Martin, but when I read the chat, they really appreciate the in-depth presentation you just have given. So thank you very much. We have one question from Femke. I think you already answered it in an earlier slide, but the question is, what are good resources to study for designing a multi-channel DAQ, data acquisition?
I would first start, so thanks first for the question, of course, but I would first identify if you have a need for a multi-channel, non-simultaneously sampled signal, or is it simultaneously sampled? That's the first decision. Do they need to be at the same time, or can they be spaced a little bit apart in time? Because one solution is far cheaper than the other one. So multiplex is far cheaper than simultaneous. The second one is, all right, go to one of the boards from the national side, because that integrates nicely, of course, with the DAQMX driver, which saves you a lot of trouble getting it to work. Some of the boards from national might not be the cheapest, but the combination always is relatively optimal. You get good hardware, great support, and a driver which really works. Read the manual. Read the manual to see, can I connect my live signals in the right way? The next step would be the introductory talks about doing measurements with DAQMX for analog input voltages or currents. Do you need a filter? There are not that many books which go heavy on the detail for data acquisition. I found a book a long time ago which does a fair job in explaining it, but it is not seeded with the DAQMX, but that comes from the previous DAQ driver, the traditional DAQ driver. And let me get it for you. It's an old one. I think it's more than 20 years old, but it was called LabVIEW Applications and Solutions by Mr. Jamal and Bijlik, if I pronounce it correctly. And that actually explains quite a lot about the bigger things, also a bit on the analysis part. I think there are also some good manuals to be found on the national website about doing measurements or signal type of analysis, which go one step further, and they probably address acquiring the data in one of the starter chapters.
Okay.
So if you need more data, just contact me directly, and I'll help you in the right direction.
Yeah, we will put all the slides in the description of this YouTube channel. We also have the DutLUG website and the DutLUG community thread, which is an NI forum.
Yes.
You will find the slides there in a few hours, days. But they will be posted online. Martin, thank you very much for all your work, for your volunteering.
No problem at all.
We will now take a little break, and we will be back in a few moments. Thank you very much, everyone.